We're going to look at the pacemaker cells of the heart, specifically how they produce action potentials. So an action potential in a pacemaker cell is sometimes called a pacemaker potential. A pacemaker cell is going to make action potentials spontaneously. They do not need an outside trigger. They actually oscillate between action potential and no action potential on their own, and they never stop at resting membrane potential. The end of the action potential triggers the next action potential. And this is how they are able to be the pacemaker that allows us to have a heartbeat. So we're going to draw the action potential on a graph. The x-axis on the horizontal is going to represent time, and this is going to be very, very quick. And the vertical axis, the y-axis, is going to represent the membrane potential in millivolts. The lowest potential that these cells will reach is about -60. The highest potential that these cells will reach is about +10. At -40 is where the threshold for the action potential to begin occurs. The first step is a slow initial depolarization until we get to the threshold. So this step is going to start at the lowest minimum membrane potential, the -60, and slowly work its way up towards that threshold. During this step, being at the -60 is a hyperpolarized state, and that hyperpolarized voltage triggers HCN channels. These are non-specific cation channels. This channel is going to allow sodium into and out of the cell. When these HCN channels are open, sodium leaks into and out of the cell. More sodium is leaking into the cell and less sodium is leaking out. So the inside of the cell is becoming more and more positive, which is going to slowly bring the membrane potential up towards that threshold value. The second step is when the action potential begins. This is the full depolarization. Once we get to the threshold, the membrane potential does increase quickly, causing that action potential. So once the membrane hits that -40 millivolts, we cross the threshold. This triggers the action potential. By hitting that threshold, it opens voltage-gated calcium channels. So that's the green channel in the middle of the image. The calcium channels, they allow the calcium that's on the outside of the cell to come into the cell. Calcium, again, has a positive charge. It's a cation. So as the calcium rushes into the cell is going to very quickly become more and more positive. The next step is called repolarization. The maximum membrane potential is about 10, and after about 10, the membrane potential begins to drop back down towards that threshold, which is called repolarizing. The calcium channels actually just close with time. So once they've been open for a certain amount of time, they begin to close, and so now calcium can no longer come into the cell. And when we reach those higher voltages of about 10, the voltage-gated potassium channels, which are the blue channels in the picture, are going to open. The potassium channels are going to open, and those allow potassium to leave the cell. And because potassium is positive, if something positive is leaving the cell, that means that the inside of the cell is going to become less positive or more negative. So the potassium leaving causes the inside of the cell to become more negative, and that's going to allow it to drop back down towards that threshold value. The fourth and final step of the pacemaker action potential is called the minimum potential. So this is just getting that membrane potential all the way back down to that hyperpolarized -60. So you can see that it kind of comes down under the threshold to -60. This is also going to trigger the next one, so you can see it kind of start to bounce up to trigger the next action potential at the end there. Once we reach that -60 millivolts, that's going to trigger those potassium channels to go ahead and close. So that's going to prevent us from getting any lower because we're not going to allow any more potassium to leave the cell. Being at that -60 value is the hyperpolarized state. And the hyperpolarized state triggers the HCN, which is the orange non-specific cation channels, to begin to open. So you can see in the image that those channels are starting to open. They're getting ready to go back to that initial slow depolarization. So the end of step 4, where the HCN channels begin to open is going to trigger step 1 again, where the HC channels allow sodium to leak in faster than it leaves. And this is going to allow these action potential cycle to continuously repeat, causing that pacemaker rhythm of the heart.